Yeah, hi everyone. I'm Martin, this is Max. We are both engineers at Neo4j. And in the previous talk, Stefan talked about features of Open Cypher. And in this talk, we will show you how some of those features are implemented in our Cypher for Apache Spark implementation. So this is a team. So it's Max and I. And then Mats is our team lead, Stefan, former team lead, and also Philip is working on that project. So why Cypher for big data? I mean, if you know Cypher, then you probably also know Neo4j, and Neo4j is a transactional database for OLTP workloads, and that's where you typically position this database system. However, many of our customers also have data lakes and already use big data tools for data integration, so ETL, as you probably know it, and also large-scale analytical processing, so more like OLAP. And we were thinking about how can we help those people with Cypher, which they are used to because they are already customers. How can they use Cypher within those two scenarios? So, and the typical big data applications that we see is just a collection here, collect data from user interactions at websites, or typically that they use internal data from their companies and put them together to do some analytics like billing, marketing, ERP system data, and so on. Or they combine it with external data, ontological data, for example. And of course, the goal is to improve customer targeting, supply chain optimization, fraud detection, and so on. So all the graph use cases, but at large scale. So in a common framework that you see in this environment is Apache Spark, a distributed data flow system. And we thought about, okay, how can we help with Cypher? How can we help those big data analytical applications? So one pillar is data integration. So here you want to be able to use multiple large-scale data sets within your analytical program. You want to retain and reuse intermediate results between queries. You want to integrate data from multiple data sources, so not only HDFS, or in our case, Neo4j, but also maybe a relational database, and then just get it into a single program and start your analytics. And of course, you want to support heterogeneous data. And the second pillar is, of course, complex analytical processing, which means that you have building blocks that which are Cypher queries, and then you want to compose them to build up your complex workflows. And what's also nice about a system like Spark is that you can integrate our library with any other library that is already available. So like for machine learning, graph processing, GraphX, or your own domain-specific business logic. And of course, Spark itself gives you all the nice features of distributed execution on a shared nothing cluster, typically. So here we introduce CAPS. CAPS is a Scala library, Cypher on Apache Spark. And its main use case is, of course, to execute Cypher on these distributed graphs. You can integrate it in your Spark analytical pipeline. At the moment, we support different data sources. So, for example, you can pull in your data from Neo4j into the Spark environment, or you have your graph stored in HDFS or your local file system in a CSV format, which we support. And it can handle heterogeneous data, and it's already able to compose Cypher queries, which you will see later in an example and in our demo. So CAPS is built by Neo4j, and we donated this to the Open Cypher community that Stefan introduced in the previous talk. It's already released on GitHub, Apache 2.0 licensed, and we are planning a release, GA release on mid-May, where we have the supported data sources for Neo4j, HDFS, and Hive. So you can also use SQL to get data out of Hive into our system. And for the rest of 2018 or beginning of 2019, we also want to add more data sources. So for example, relational DBMS like Oracle, Postgres, and so on. And also support systems that are basically Gremlin focused, but we have a translator from Cypher for Gremlin, which you can use to also use data out of those systems. Okay, so let's get a bit more technical. So what's the architecture? So as you see on the top, this is a regular Cypher query. It's just looking for a person which loves a specific system, in this case Neo4j, and there's an optional match, so this person might also love Spark. And we want to return the person and the two systems. So we have a multi-layer architecture within CAPS. We start, of course, with parsing the query. For that, we use the Open Cypher frontend, which is a shared module, which is also used by Neo4j. So that gives you take the string in and get the abstract syntax tree out. And it does all the parsing, rewriting of the query, and some algebraic optimization. Then there's CAPS. CAPS is mainly used to translate the AST, the abstract syntax tree, into something that can be executed on data frames, which is the abstraction that Spark gives you. So it's basically a translator between those two things. And it also gives you the ability to import data, of course, export data. And we also have schema and type handling because, as you might know, data frames have a fixed schema, and a Neo4j or property graph in general doesn't have a fixed schema. So there needs to be some handling between those two worlds, which I will explain later a bit. And then after CAPS, when we have our data frame program, we just hand it over to Spark, and Spark has this nice thing called the Catalyst Optimizer, which is a rule-based optimizer for query optimization, which gives you some improvements on your runtimes, probably. And then at the end, of course, the Spark runtime, which executes the query on your cluster. So this is the high-level view of the system. Okay, so we had some. You have some, as I already mentioned, there are some differences between Neo4j and Apache Spark, or in specific the data frame API. So at first, let's talk about the graph format. Neo4j, as you might know, is a so-called native graph database, which means it's built up from bottom to top, optimized for graph operations. So the storage layout and up to the query language is all optimized for graphs. Whereas data frames, which is the abstraction in Apache Spark, is more like a table in a relational DBMS. So it has a fixed schema. You have the relational operators like join, union, and so on. And that's, of course, a gap there. Yeah, as I mentioned, the operators, we have relation operators on the Spark side, and we have native graph operators on the Neo4j side. So, for example, expand is an operator where you get all the relationships of a specific node, or var expand to compute a variable length path expression. So, like someone knows someone over 1 to 10 hops. Then the schema, I already mentioned, we have schema optionality on Neo4j side. So we have some constraints on the schema, but you can also have even for the same label for a node, you can have a different kind of schema for that, so different kind of properties. On the Spark side, this is all fixed. And then, of course, there's the type system. We have the Cypher type system, and on the other hand, the Spark SQL type system, which are not compatible by default, so those have also to be mapped. So let's talk about a few of those challenges. At first, about the schema. So as I said, we require a schema for Spark data frames. And if you use, for example, our HDFS data source, which I said is a CSV, then of course you have already a schema available, which is explicitly defined. And we can just derive it from there. If you, for example, load your data out of Neo4j, we implicitly infer the schema while loading the data. So we build it up while we see the data. And for example, if you look at this graph here, I hope you can see some of it. It's not that complicated, just two persons that know each other, and they love different systems. And for that example, a schema would look like this. You have the node labels, for example, person. And a person has two properties, name, which is of type string, and year of birth, which is of type integer. And it's nullable because not all persons have the year of birth property key. And then there's also the employee label. And the employee is an implied label. So if someone is an employee, he also is a person, because those two always appear together. So person employee also has the name property in that example here. And then the same for relationship types. You have the knows relationship between those two persons, which has a specific property key since of type integer. The second challenge is the graph representation. So from a logical point of view, you have the property graph. So how do you represent that in data frames? And data frames, as I said, are tables. So we chose the concept of node and relationship tables, which are constructed by label. So in that example, we have one table for persons and one table for the systems that you see on the bottom. And the employee, for example, which I said is an implied label, so it always occurs together with the person label, is just an additional column in that node table here. It's a Boolean column, so it's just true, false if that person is also an employee. And then you have all the properties here, so like you would also model it in a relational database, of course. So, and then you have null properties for those optional property keys here. Same for relationships, relationship table, as we call it, where you, in addition, also have the source and the target or start and end node identifier of this relationship, and then also the properties that this relationship might have. Okay, the next challenge is query translation. So again, we have our Cypher query here. And the physical view is, of course, query optimization or query engine handling in general. So we have on the left side our input, which are the node tables that I just showed you, and then we have a series of operators, and in the end we have a result, which is the result of our query. So this is basically where the magic happens within the system, and today I want to explain some of this magic at least. So on the left side you see the same architecture as before. It's a high-level view of the system. Here is CAPS, and within CAPS we have 4 phases of query planning. So the first phase is so-called intermediate language phase. It's an intermediate representation of the query, which is backend agnostic, because one other goal besides doing that on Spark is being able to port this project to other backend systems. So maybe an in-memory system or Apache Flink, for example, something like that. So this is a backend agnostic query representation at first. So we translate the AST into that, and then we start with logical planning. So this is still graph-specific operators. So on the logical planning side, you still have operators like expand, var expand that I mentioned before, and we do some basic additional optimization to what the front end is already doing at this place. Then we have the flat planning. The flat planning is the step where we translate or where we compute the column layout of the resulting data frames. So if you, for example, do an expand, so go from a node to their relationships, then you need to compute the column layout for the resulting data frame, so the schema basically. And this is what the flat planning does. And then in the physical planning, this is where we actually translate the graph native operators like expand, var expand, and so on into data frame operations like join, select, distinct, and so on. And then, of course, like I said before, this is handed over to the Spark engine again, is being optimized by the Catalyst optimizer and executed by the runtime. Okay, and when you finish a query, you have, of course, the result available, which is again a data frame, which we call a Cypher result, which contains each row represents one result. So in that case, we wanted to return the user and the 2 systems. So for example, Alice here, as you can see, loves Spark and Neo4j, and Bob only loves Neo4j. So the rest of the row here is filled up with null values. Okay, so now that we know some internals at least of CAPS, we want to talk about the API before we show you the demo. So we try to adapt our API to, or make it pretty similar to what Spark already provides to you, or with the data frame API, to make it especially easy for people that are used to Spark to also use CAPS. The central point is the so-called CAPS session, as analogous to the Spark session. And this is the minimal program to run a Cypher query on Apache Spark. So in the first line, for example, we just create a local session which instantiates the Spark cluster and so on. And then in the second line, we specify a data source by just saying session.readFrom, and then we give them a URI where the scheme defines which kind of data source it is. So in that case, you might not read it, but it's HDFS plus CSV, which internally triggers the right code path to read to get the right reader for this kind of graph. And then the address where it's stored within HDFS. On line 4, we actually, line 4 is actually line 3, but whatever. It actually triggers the query. And on line 4, we trigger we print the result, which would lead to that console output that you can see here, as you are used to from Neo4j. Then there's the second example, which of course is just available for the first row to read. So on the left side, yeah, sorry about that, but on the left side, this is just regular Spark code to create data frames. On top, just trust me, this constructs a node data frame and this relationship data frame with some schema. And then on the right side, this is the program that actually uses those data frames to run a query on it. And we use a concept called entity mapping, which is basically just a mapping between the column names in the Spark data frame and the concepts that we need to construct nodes and relationships from that. So you have to tell us where to find the node ID, for example, where to find a specific property key in which column, and same for relationships with addition of course, start and end node key. So it's pretty simple. So, and that's the goal of an API. Stefan talked before about multiple graphs. This is an example that is also currently available in CAPS that you can run, which involves multiple graphs. Max will give you a more advanced example later, but it's just to give you the idea. So what we do here is we take two graphs, we mount the first one from HDFS, and the second one is coming from Neo4j, indicated by this bold scheme in the URI, and two queries to get the data out of Neo4j, and we store them at two paths, my HDFS graph and my Neo graph. And then within the query, we can say, from my HDFS graph, give me all the employees, and from my Neo4j graph, give me all the persons, and then join those two graphs where the users, the persons and the employee have a matching email address. So we do data integration basically. We have two graphs separate, HDFS, Neo4j, and we join them together based on some knowledge that we have about those two graphs. And then we return a new graph, which creates a new relationship between the employee and the persons that match, and create a new relationship called same as. And then this graph is used with an additional query that you can see here. So it's also an example for composition, because this is the first query, this is the second query that we trigger on the result of the first one. Okay, this is the concept, and Max now will show you a more advanced example, a running example of that.
Okay, so before we can start the example, I just want to set you all up with the scenario we are talking about. So let's assume we are a company and we want to do a marketing campaign in specific metropolitan areas. And we have access to two data sets. One data set is a social network. It's an generated social network in our case, which we split up into two regions. So we have our social network is once partitioned into the North America part and the Europe part, and we store it in two Neo4j databases just for scalability and for performance optimization. And then on the other side, we have a customer data set. So it's customers who have bought products. Those products are also categorized into product categories. And on the social network side, of course, we have people who know one another, who live in certain cities, and they're interested in different interests. And as you can already see, we have a shared attribute across those data sets. So people on the social network side, as well as customers on the product side, both have an email address. And this is where we can connect those data sets. So what we do is we assume that if a person on the social network side and a customer on the product side have the same email address, they are the same person in reality. So they are the same, they represent the same entity. And yeah, I forgot to mention that the product data set is stored in HDFS, just to make this example a bit more complex or like diverse. So, and what we want to do is we load the data from their corresponding data source, as I said, Neo4j and HDFS. We extract subgraphs that only contain the data concerning those metropolitan areas we want to target. In our case, this is New York City, San Francisco, Berlin, and Stockholm. And then we merge those two graphs on the email attribute, and then we compute recommendations. So we want to recommend users products that their friends have bought and which as their friends and the user both are interested in. Yes, and that's basically our setting for the demo. And now let's switch to Zeppelin. So Zeppelin is a data science tool which allows you to run Spark queries in an interactive fashion. And we have adapted CAPS so that we somewhat support Zeppelin, and we can use it for our demo. Is it big enough? Is it readable from like at least some places in this room, or should I increase the font size even more? Okay, I'll leave it as it is. So what we've already done is we've imported all the all the CAPS libraries. It's like the CAPS session, and we have this special Zeppelin support class here just for the Zeppelin, and we've already created the CAPS session. And what we start with is loading the data sets. So we first read our graphs from Neo4j. This is done in those first 2 lines. Just run it here because sometimes it takes a while. And so we read the data from Neo4j from the 2 regions, and we read the data from our product data set, which is done here. So you see this is using bold, which is the Neo4j scheme, and then we have HDFS and CSV. So we tell our system this format is stored in HDFS and uses our custom CSV format. And then what we do here, this is somewhat analogous to the mount call that Martin showed previously. So we have our graph, and now we store it in the session under a certain name, or in our case, currently this is in a URI, so we can later use it from within a Cypher query. So we can, from within the Cypher query, we can reference that graph, change our input graph, and now read from a different source. So this worked, I guess, yes. And now let's start with some simple queries to show you just this is like the Cypher 9 Cypher capabilities that we already support. So let's take our social networks and have a look at the distribution of interest in our cities. So both for New York City and San Francisco, as well as Stockholm and Berlin. And what we do here is we select all people and their interests, and then we group by city name and interest. Let's have a look what people in those cities like. So it's also to kind of demonstrate how nicely this integrates with Zeppelin. So you can do your Cypher queries, which are quite readable, and then you get a quite nice visualization of that. So what we see is here in New York City, the interests are more or less evenly distributed. San Francisco is somewhat more old school. They seem to like videos more than DVD. I guess this is like real videos, like VHS. And they don't read as many books. But I mean, it's artificial data, so it's just for the fun. Looks almost the same for Berlin and Stockholm. What we do now is, to make our lives a bit more easier, we extract those metropolitan areas. So we don't want to look at all the cities that are available in our dataset, but as I said, we just want to target those 4 cities. So we extract graphs of people who live in one of our target cities. And if 2 people live in the same city and know one another about 1 or 2 hops, that is, they are friends or friends of friends, then we create a new graph with an edge between those people. So from now on, they live in the same like social circle. And then we return that graph. Let's run those queries. And here we have not a table representation anymore, because we don't really return a tabular result, but we return a graph result. We return a new graph. So what we get here is visualization of the new graph. You see those 2 communities. I guess one of them represents all the people living in New York City. The other one, all the people living in San Francisco. And they're all somewhat connected if they know one another or their friends know one another. To run this as well. Now, what we now do is we combine those 2 graphs. So far, we always worked with the 2 different social network data sets. So we had the one for New York, the one for Europe. And we now want to combine them into a single graph, just because it makes life easier for us. And we, again, store this combined graph in our session using the Friends URI. And now we do merge the 2 data sets. This is where the multiple graph capabilities come in handy now. So we start by reading from our friends graph. So this is what we use now. We use this feature graph at friends. So we tell the system, for now I want to read from the friends graph. And we find all people and access their email address. And then we switch our input graph. From now on, we keep the results that we have computed so far, but everything that is going to happen now, or reads that are going to happen now, are done using the products graph. So again, we find all users and their email addresses, and now we do a cross product, or a value join. So we find people and users that have the same email address. And for every tuple that we create a new graph with an is edge. So user is a person, is the same person. So up until now, we have done our ETL. So we had. Didn't I do that? No, I did it already. So this was all ETL stuff. So we had our input data, our more or less raw input data, and we've transformed it so that we can now do our analysis. First, we have to combine all the data into a single graph. Just makes it easier again, because we also want to access the person attributes and their interests and stuff like that. So we create one large graph and use this graph to do our analysis. So what we do is we find people that are in the same social circle and like a certain interest. And then if the user is the same as a user, or if the person in the social network is the same as a user in our products database and has brought a certain product that belongs into a category which his friend likes, then we recommend his friend this product. And then we also rank those recommendations by the number, or by the ranking or rating of the product, and how helpful those votes actually are, or how many votes a certain rating has gotten. Yes, and then we execute this and can actually visualize it in a table. This takes a while. I'm running it locally on my laptop right now. It's a graph with a couple of thousand nodes and a couple of 10 or 100,000 edges. Yeah, and as I said, we started with two raw input data sets. We combined them using some ETL capabilities, and then using the same language that is Cypher, we could also do an analysis of the data and do some analytics. Here we are. We now have a table with recommendations. So what we see is we could recommend Billy Anderson with a certain email address, and we should recommend him to buy the book The Life of Pi. Yeah, that's all for the demo for so far, and also for our talk. As we said, no, that's this slide. We thank you for listening, and we welcome you all to check out our project. It's on GitHub, as we said. It's open source licensed. You can use it. It's still in alpha, so we are constantly changing stuff. So don't rely too much on certain details. We are finalizing the API right now, so this is somewhat stable already. And not only if you're interested in Apache for Spark, but also if you're interested in implementing Cypher on another system, check out our project. We try to keep our project in a way that it's easy to reuse all parts, up to the depending on how your backend is structured. You could if your backend is relational also, then you can use quite a lot of our project, all the schema translations, all the header calculations. Or if you just want to do your in-memory database, then you can just use the front end, the intermediate representation, and then you're already quite a far step from just having to do all the implementation on your own. So both if you're interested in Spark or want to implement Cypher, check out our project and contact us if you have any questions. Thank you.
Please stay seated for the questions, so 5 minutes of questions. Anyone for Max or Martin?
No.
Okay, if there are no questions, Max. Oh, there's one.
Okay. What did you say?
Why Scala?
Because Cypher is written in Scala, and the question was why Scala? And yeah, it's Spark. So Spark is easiest accessible from Scala. It's also possible with Java, but it's just nicer with Scala. And also the rest of Cypher on the Neo4j side is also written in Scala, so just makes our life a whole lot easier.
Is that a new version of Zeppelin that you're using, or do you use an extension?
Yeah, the Zeppelin, yeah, the version of Zeppelin is a preview version, so 0.8.0 snapshot or something like this. just because it has this nice network or like graph representation. On our website, on the GitHub project, there's a wiki link on how you can integrate Zeppelin, caps with Zeppelin, and we explain also, I think, in some short detail how you can build the snapshot version. But you can also use it with the current stable release.
By the way, the Zeppelin support for graphs and Neo4j was done by one of our community members in Italy, and as soon as Zeppelin 8 is out, or 08 is out, you can all use graphs with Zeppelin, which is really fun. Just also general. Yeah?
Do you have plan? Do you know or have plan how to efficiently distribute the graph and the Spark to improve the Spark capabilities to make parallel computation on the multiple nodes?
So the question was if we already looked into, I guess what you mean is graph partitioning, so how to smartly partition the graph over HDFS. Not yet, but it's on our roadmap for the next time. So it's part of our performance tuning, of course, and this is mostly related to performance, to have a good partitioning of the input graph and also recompute partitioning during query execution. So that's on the roadmap. But currently we only rely on what Spark gives us by default, which is, I guess, hash partitioning. Yeah.
Okay.
You said so the OpenCypher implementation for this is in Scala. Does that mean if you were to want to write your own OpenCypher implementation to interface with your own sources, is there only libraries and tools available for Scala, like the parser or whatever? Is it only for Scala, or are there other language libraries available?
I can take this maybe. And so the question was, is the only tooling for writing your own implementation? Oh yeah, I need to see. So the question was if the tooling available for writing your own Cypher implementation, if that's only available in Scala. That's not true. So the TCK is language agnostic. So the set of test suites that your implementation needs to kind of conform to be a good implementation is completely language agnostic. Also the EBNF or the grammar is available as an EBNF grammar and as an ANTLER grammar. So you could easily generate a parser for all kinds of languages. But the layer beyond that is currently only available in Scala in an open source implementation. But I know of one more open source implementation or implementation that's going to be open source that's coming out. It's actually not from Neo. And so, watch the space. I think more things are going to happen, right? So that's the other side of it. But you get some starting tooling from us. So you could do it if you wanted to, right?
Cool. Then thank you so much for your time. Next in